Far beneath the sunlit surface of our planet lies a realm of eternal darkness and crushing pressure, a vast frontier that remains more mysterious than the dark side of the moon. What if the key to unlocking the deepest secrets of Earth's oceans requires us to surrender our physical presence entirely? The answer lies not in holding our breath, but in building a bridge between human curiosity and artificial intelligence. This is the dawn of a new era in deep-sea exploration, driven by an intricate dance of human design and automated systems. For centuries, our fragile biology kept the abyssal plains out of reach, guarded by thousands of pounds of pressure per square inch. Now we are projecting our senses into the void through advanced robotics, creating a binary bridge where silicon and steel endure what flesh and bone cannot. The history of oceanography was once defined by profound limitations, tethered to the surface by the physical constraints of human endurance. Early submersibles offered only fleeting glimpses through tiny portholes, capturing a fraction of a percent of the ocean floor. The sheer scale of the unknown demanded a radical shift in how we observe, measure, and interact with extreme environments, paving the way for machines to become our permanent deep-sea avatars. Today, that radical shift is embodied by autonomous underwater vehicles, or AUVs, engineered to descend into the most unforgiving regions on Earth. At the forefront of this revolution is the Woods Hole Oceanographic Institution, deploying remarkable machines like the AUV Sentry and the remotely operated vehicle, ROV Jason. These are not mere cameras on strings, but sophisticated, untethered explorers capable of making independent decisions miles beneath the rolling waves. To navigate these pitch-black depths, these vehicles rely heavily on machine learning, a branch of artificial intelligence where algorithms improve their performance by analyzing vast amounts of data over time. Down in the Hadal zones, the deepest trenches of the ocean, there is no GPS signal and no remote control. The Sentry must map its own path, avoiding jagged underwater cliffs and adjusting its buoyancy entirely on its own. Yet the true magic happens when this autonomous data collection meets human scientific inquiry. As these submersibles glide silently over the seabed, they gather unprecedented volumes of high-resolution sonar, chemical readings, and optical imagery. The sheer influx of sensory data would take human researchers decades to parse manually, but the digital pioneers have set a course that fundamentally accelerates the pace of biological and geological discovery. This rapid processing is made possible by neural networks, complex computing systems inspired by the human brain that are designed to recognize intricate patterns within massive datasets. Embedded within the robotics systems, these networks sift through millions of acoustic pings and shadowy photographs in real time. They are trained to ignore the static of the deep and highlight anomalies, flagging a strange chemical plume or an unusual shadow for further investigation. The impact of this real-time anomaly detection is reshaping our understanding of marine biodiversity at a staggering rate. By pinpointing the unique biological signatures of previously unknown species, the AI acts as a digital bloodhound, leading ROV Jason directly to vibrant ecosystems hidden in the abyss. We are no longer blindly casting nets into the dark, but surgically exploring thriving communities of life that defy our traditional understanding of biology. Consider the stark contrast between human perception and machine capability in this environment. A human diver, even in a specialized suit, is limited by the narrow beam of a flashlight and the rapid depletion of oxygen. The robotic explorer, however, perceives the ocean in multiple dimensions simultaneously, tasting the water chemistry, feeling the magnetic shifts, and seeing the topography in highly detailed 3D maps, all without ever needing to surface. This multisensory approach has led to staggering revelations, particularly around hydrothermal vents where superheated, mineral-rich water erupts from the Earth's crust. Here, AI algorithms have helped identify entirely new classifications of extremophiles, organisms that thrive on toxic chemicals rather than sunlight. Finding life where it theoretically should not exist challenges our fundamental assumptions, proving that the ocean floor is not a barren wasteland, but a vibrant alien world right beneath our feet. The implications of these discoveries extend far beyond the classification of new marine species. These abyssal ecosystems play a critical, previously underestimated role in regulating Earth's climate and driving the global carbon cycle. By mapping vast stretches of the ocean floor, human-machine collaboration provides the essential data needed to understand how the deep ocean sequesters carbon, offering vital insights into our planet's complex environmental machinery during an era of rapid change. Leading marine biologists and oceanographers now view these advanced algorithms not as replacements, but as indispensable partners in the scientific method. The AI highlights the needle in the haystack, allowing the human scientists at Woods Hole to focus their expertise on understanding the needle itself. This dynamic illustrates the core strength of the binary bridge, where computational brute force is perfectly balanced by human intuition, contextual understanding, and scientific curiosity. However, the unprecedented ability to map and catalog the deep ocean brings profound responsibilities. As we illuminate these untouched ecosystems, we also expose them to the potential threats of deep-sea mining and industrial exploitation. The same detailed 3D maps that guide biologists to new species of ghost octopuses and glass sponges can also guide extraction companies to lucrative deposits of rare earth metals, sparking a fierce debate over conservation and commerce. The subtle human oversight fueling ethical deployment becomes the crucial barrier between discovery and destruction. We are tasked with programming these machines not just for efficiency, but with parameters that respect the fragile nature of the environments they traverse. The algorithms can calculate the most efficient path to a mineral deposit, but it requires human wisdom to decide whether that path should be taken at the cost of an ancient, slow-growing coral reef. This intersection of capability and consequence forces us to redefine the very nature of exploration. When an autonomous vehicle, miles beyond human communication, recognizes and photographs a species never before seen by human eyes, who is the true discoverer? The machine that captured the light, or the human who wrote the code? It is a shared triumph, an intertwined legacy where the creator and the creation expand the boundaries of knowledge together. And this is just the beginning of the aquatic automation revolution. Researchers are currently developing swarm robotics, where dozens of smaller AI-driven submersibles will communicate and coordinate with one another, sweeping across the ocean floor like a flock of birds. This collective intelligence will map the remaining unexplored regions of the seabed exponentially faster, transforming our fragmented understanding of the deep ocean into a comprehensive, high-resolution global picture. Driving this next phase is the rapid advancement of edge computing within the underwater vehicles themselves. Instead of merely collecting raw data and waiting for retrieval, the newest iterations of Sentry and its successors process complex information entirely on board. The algorithm's shadow still loomed, but now it operates with unprecedented independence, deciding in a fraction of a second whether a geological formation warrants a closer look or a physical sample. The technologies perfected in the crushing depths of our own planet are already laying the groundwork for off-world exploration. The challenges of navigating the Mariana Trench mirror the obstacles of exploring the subsurface oceans of Jupiter's moon, Europa, or Saturn's Enceladus. The autonomous navigation, the real-time anomaly detection, and the resilient engineering forged in Earth's oceans are the exact tools humanity will use to search for extraterrestrial life in the decades to come. It is a striking paradox that we often look to the stars with wonder while ignoring the alien landscapes hidden beneath our own waves. Space exploration commands massive budgets and global attention, yet the deep sea remains Earth's largest and least understood habitat. The integration of advanced robotics is slowly correcting this imbalance, proving that we do not need a rocket to find bizarre, otherworldly life forms or to push the absolute limits of engineering. Beyond the raw data and the scientific breakthroughs, there is an unexpected emotional resonance to this human-machine interface. When operators pilot ROV Jason through a field of hydrothermal chimneys, watching the high-definition feed in a control room thousands of miles away, they experience a profound sense of presence. The machine becomes an extension of the human nervous system, translating the cold, dark pressure of the abyss into a shared experience of awe. The sheer volume of biological novelty being uncovered is forcing taxonomists to rewrite textbooks on a monthly basis. From ethereal jellyfish that glow with bioluminescence to armored snails that incorporate iron into their shells, the AI-assisted discoveries reveal an evolutionary creativity that defies imagination. We are realizing that the deep ocean is not a harsh, empty desert, but a crucible of life, overflowing with genetic secrets that could revolutionize medicine and biotechnology. The lessons from that early research never faded. The spirit of the Polynesian navigators and the intrepid scientists of the HMS Challenger expedition lives on, translated into lines of code and titanium pressure spheres. They charted the surface with astrolabes and plumb lines, while we mapped the abyss with acoustic telemetry and neural networks. The medium has changed drastically, but the fundamental human drive to map the unknown remains the beating heart of the endeavor. What if the ultimate answer to our origins lies waiting in the dark? Many scientists hypothesize that life on Earth may have begun around the very hydrothermal vents that these autonomous vehicles are currently mapping. By studying how extremophiles survive in these toxic, high-pressure environments, the artificial intelligence we created might just help us uncover the precise biological spark that ignited life on our planet billions of years ago. Ultimately, this technological convergence is democratizing access to the deep sea. The massive datasets collected by these robotic explorers are increasingly made available to the global scientific community and the public. A student in a landlocked classroom can now study a 3D model of a newly discovered Hadal Trench, participating in the process of discovery and fostering a new generation of ocean stewards connected to the sea through a digital umbilical cord. The deep ocean remains Earth's most mysterious frontier, but the shadows are finally receding. Through the intricate partnership of human intellect and artificial intelligence, we are unlocking a world of eternal darkness, revealing vital climate data and astonishing new marine species. This is the ultimate promise of the binary bridge, a testament to how human ingenuity, amplified by machine intelligence, is not just discovering new life, but fundamentally expanding what it means to explore.